一个是 hypoxia chamber 在做 cell culture 与 tissue culture 的应用。那最后一个是 gel count， 比较是偏向于在mammalian cell 的 colony 我们在做一些肿瘤的菌落这部分。那因为开始前我们时间有限，我想先请问一下，在这边做肿瘤相关研究的，可以稍微举个手吗？一个，一个。那做比较偏组织血流跟血氧这一块会有关系的有哪些？可以举手一下。1、2、3、4、5、6、7，比较多。那在养细胞，如果说你们有碰到，例如说你们要做一些 hypoxia 的环境的，会不会有这样子的需求？OK， 好，那这样子，因为我们刚刚前面也有稍微讨论一下，就是我会请我们的今天原厂的 manager Petra 呢，他会先从血流血氧开始讲起。那后面因为刚好上2个星期前 Nobel Prize 也 release 出来了，有稍微提到了一些我们在养细胞的环境的部分。那接下来第2个主题我们会进入到 hypoxia chamber 这个地方。那 gel count 我也会请他稍微带一些资讯给大家。那如果说结束之后你们有更进一步的问题想要讨论，会有一些想要更了解、深度了解的话，后面我们有 Q&A 时间，我们可以再来讨论。Okay, now I'm going to speak English. So everyone here, English is okay. I'm asking Petra to speak slower. Okay. And yes, and good afternoon everyone. And I'm I feel pleasure to have a workshop today in the translation center here. And also I'm very happy we invited the international product manager Petra Meyer.
Yeah,
Sorry.
Perfect.
Okay, from Oxford Optronics, and she will bring some product information and application for us this afternoon. And I think we will start from the OxyLite Oxyflo application, and the second is about the hypoxia chamber, and latest is our gel count. So let me introduce Petra.
Thank you very much for the introduction, Jerry. And as Jerry said, I'll try and speak slow. Normally I speak very fast. So if I'm getting too fast, please raise a hand and say, speak slower, yeah? If I get excited, so let me know. So as Jerry said, I'm from the company Oxford Optronics. Actually, can we dim the lights in the front a bit? Yeah, is it better to see? Yeah? Okay, good. So I'm from the company Oxford Optronics, and I'm working for the company for the last 20 years, especially with the PO2 monitors with the OxyLite, the laser Doppler monitor Oxyflo and hypoxylite. So I'll be mainly talking about that today, because I think it's also, most of the people in this room here will be interested in that topic. So how do we measure oxygenation and microvascular blood perfusion in the tissue? I'll explain how the PO2 monitor works, the OxyLite, and I speak a bit about laser Doppler. We do have an OxyLite here today, and we've been doing one experiment already this morning, and we will do another one this afternoon. And what I just would like to mention before we start, because sometimes people are a bit confused, we measure the dissolved oxygen with our PO2 monitor. We do not measure oxygen saturation, which is the oxygen bound to the hemoglobin. They're different. That's mainly used in hospitals with patients. When you get an oximeter on your finger to measure blood saturation, that's what people measure. But we measure the oxygen which is freely available to the cells to be consumed. So this is how the OxyLite looks. We do have a 2-channel system, which means you can connect 2 oxygen sensors and combined with 2 temperature sensors. Or we have a 4-channel system where you also can measure on the other side. And this instrument is used for in vivo or also in vitro monitoring in cell culture if you want to know what your partial oxygen pressure is in the medium in which the cells are growing. The laser Doppler, it's a traditional laser Doppler system to measure microvascular blood perfusion, and it's only for in vivo monitoring. So it's very often used for stroke models, for ischemia reperfusion studies. And the values you get are relative values. They're not absolute values. It's an artificial unit. The OxyLite is our third generation now, over the last 20 years. It's the easiest to use monitor because you have like pre-calibrated sensors. You just plug the sensor in, it has the calibration data stored. There's no calibration necessary. It comes from, originally it was developed in a cancer lab, so it was important to get a very good resolution at the low oxygen readings. So it's very accurate there in the physiologic range or physiological range. The dynamic range goes up to 200 millimeter mercury, which means it's above the atmospheric oxygen we measure, that would be 159 millimeter mercury, so the range is sufficient. It has a touch screen, as you can see here. You can connect it if you're using AD Instruments Power Lab or LabChart software. You can connect it directly with a USB cable to the computer. If you don't have a Power Lab LabChart software, you can use any other data acquisition system which has analog inputs from 0 to 5 volt. Yeah? So you have the flexibility to do that. And the advantage of that system is you can connect several sensors, so you can do simultaneous measurements. So if you have a stroke model, you can have one sensor in the damaged brain half and one in the other half, for example. Or if you look at some organs in the body, you can have one sensor in the muscle, one in the liver, one in the bladder, one in the kidney cortex. So you can see how the body and the different organs react to challenges, to shock, hemorrhagic shock, septic shock, or so on, at the same time. And you will see differences on how each organ shuts down or when it shuts down. We do have various types of sensors. The technology is not like the old conventional clock type electrodes where you consume oxygen while you're taking a measurement. In this case, the oxygen will diffuse into the tip and out again and make an equilibrium with the surrounding tissue area. And it does not consume oxygen while it's doing it. It just makes an equilibrium. And the response time of the sensor is dependent on how fast the oxygen goes into that silicon matrix and out again. Yeah? So we have the glass fiber, we have the silicon matrix, and we have a phosphorescent dye inside the sensor. Inside that silicon matrix, it does not go into the tissue. Yeah? So that's an old picture. Now we have a greenish instead of blue light come out of the glass fiber to the sensor tip. It excites the electrons on the phosphorescent dye, which jump to a different energy level. And when the electrons jump back, they emit orange light. And the orange light goes back through the same glass fiber to the machine and is detected. So if you have no oxygen there, the orange light might light about 3.5 microseconds. If you have 10% oxygen there, the lifetime of the light is shortened, is quenched, and you might just have 1 microsecond. So we calibrate each sensor in the presence of the oxygen to get a calibration profile and to measure the lifetime of the light, how long it's alive, so to speak. We do not measure intensity because that would be less accurate. Okay? We do offer those sensors with temperature because the partial oxygen pressure needs a temperature value to correct for the temperature, so to speak. Yeah? So you can have just an oxygen sensor and the instrument will receive a manual input from you telling I have a controlled experiment, my animal is always 37 degrees, I have it on a heating pad. So you can use 37 degrees, but if your animal has fever, heat stroke, shock, the temperature might go up or down. You might want to measure oxygen at the same time, temperature at the same time. That's why we have also sensors with temperature. I'll just reach that round. Sorry. That's the smallest sensor we have. It's a demo. You can touch, not break, but you can bend and feel how it maybe can be used or so. So this is oxygen only. That's the smallest one we do. And just one more. So I'll just do the next picture. The laser Doppler, I'm not talking much about that right now. If there are questions, I can answer them later. As I said, it's a standard monitor to measure microvascular blood perfusion. You have 2 glass fibers, not one, like with the oxygen. So you have one where the light comes out and one where the light goes back. And depending if there are any moving particles, the light will be reflected with a different wavelength, which is the laser Doppler shift, and that's what we measure. Oxford Optronics is the only company in the world which offers a combined sensor, which measures oxygen and temperature and laser Doppler in one sensor. And the sensor splits at the end in 2 connectors which go into 2 different devices. So it's a very unique setup. It's very popular in like rat brain research, for example, because the sensor is very small. You can target it to one spot and you don't have so many cables when you're practically working. Yeah. So this would be, we call them triple sensors, so that's oxygen, temperature, and laser Doppler, I think. Yeah, it's a bit strong. So the red, you can see a red line, that's the thermocouple, which measures the temperature. So let's start here. So the applications, and then I'm very open for questions and to tell you how to introduce them. The sensors, we come originally from tumor cancer research, where people look at cellular resistance to therapy during extreme hypoxia. In the tumor, sometimes you only find maybe 1 millimeter mercury, or maybe even 0 if it's already necrotic. Yeah. Outside, so on the outside of the tumor, you get a higher oxygen value because obviously the tumor is better vascularized. Yeah. Our second largest area is the cerebral monitoring. As I said, the sensors are so small, so they are ideal for insertion into rat brain with a stereotactic setup. And because the brain atlas is very well mapped, people really can target where they want to measure. also very popular and at the moment is vital organ monitoring, especially for us at the moment it's kidney or acute kidney failure, where you place two sensors, one in the cortex, one in the kidney medulla, and maybe one in the urine. And then, like during cardiac bypass, for example, you can look if that animal would go into heart failure, into kidney failure afterwards, because during cardiac surgery, about 30% of patients have kidney failure afterwards. So they're looking at the moment to be able to predict if the animal would go into kidney failure or not. We have also customers in plastic surgery, in wound healing, to look at fluid transfer to see if it grows again on. Also ophthalmology, isolated eye or rabbit eyes on the rabbit. And more like in vitro dissolved oxygen monitoring, especially like tissue engineering, 3D cell constructs, like organoid constructs, microchip, like liver on a microchip or so. So people are interested in that because they need to find out if their cells have still enough oxygen in the center of their scaffolds or organoids, and if they're well enough perfused with the buffer or so they run through.
Okay. One question.
Yeah.
In the solid tumor,
yeah.
How could we inject or put the probe inside the tumor?
I'm doing fantastic drawings. I tried. So, normally you have the mouse, yeah, or rat, and you have the tumor here. So that's the hypoxic area, maybe. So I'll pretend that's the sensor. Okay. I usually you cut the skin to see the tumor.
Yes.
And then there's several methods. One would be you use an angiocath. You use an angiocath.
Okay.
Yeah. And I like to use it horizontally to the table because you can support the sensor. So depending on what question you want to ask, if you want to map the tumor, you would go with the angiocath nearly to the end of the tumor, pull the needle out, and then put that glass fiber sensor in.
I got it.
And then you can pull both. You can pull the sheath back. Because one can remove the lure lock. It's glued on at the dummy sensors, but you can move it off. So you can like push that angiocath back out and you just have the sensor in the tissue. And then if that's the sensor, you then can slowly pull it back. And you get high reading, low reading, low reading, and high, and you get a profile. And then you could do the track again from a different angle. That's one option, and then you know how hypoxic it is and where it is hypoxic. And if you then want to treat, you can go like back in and say, I want one sensor in the hypoxic area, and I want one in the vascularized area here, and then you fix them, and then you can give a drug or something and see what happens. Yeah, that would be one option. The other one is you use the angiocath again, you go in, you go out on the other side. You introduce the oxygen fiber on this side, go in and pull the thing out. That's a retrograde one, that's even more elegant. Yeah, so it depends how your working area is. Yeah. Alternatively, you could come in just from the top and need to support it with a holder. Yeah. And some of our customers that use a hypodermic needle, so no sheath, just a needle, make a track, pull it out, and then you get a little blood clot, and then you try and find the hole. But that's a bit tricky, and you might break the sensor. Yeah. So these are 3 options, so to speak, you could use. But do not use a hypodermic needle and then try and get the sensor in, because it's inside different from the sheath, and you damage the sensor quite likely. And it's good for us if you damage the sensor, but bad for you. We don't want that. Yeah. So because you have to buy a new one, so it's more expensive. So it's better if you use an angiocardic. Okay. Any other questions so far? Okay. So because we're in a bit of a rush today, so we're working in the physiological range. The laser Doppler I haven't spoken much about, has a special filter inside, which if you measure vital organs, which removes the breathing artifacts, the movement artifacts, yeah. With the oxygen, that's not so crucial, but it's important in the laser Doppler. We offer the combined sensors. You can work with the instrument with the touch screen. Sensors are pre-calibrated, the laser Doppler sensors too. There's no oxygen consumption, and the calibration stability is 1 year. The sensors are minimally invasive, which means the oxygen sensor has to be in the tissue. Yeah, it can't be outside, because then you measure atmospheric oxygen. So it has to be inside, but because it's very small, it's minimally invasive. And also the sensors without the temperature are MRI compatible, because they don't have any metal there. So what we do is we make 8-meter long cables. So the instrument, the sensors can go through the cable shaft into the magnet, and the instrument stays quite far away outside that Gauss curve. Okay. As I said, we have the automatic temperature compensation or manual input, and the 2-channel system can be upgraded to a 4-channel system, and you have the mix and match options. For example, I said, well, I want a 4-channel oxygen monitor, but I only need 2 laser Doppler, or you just buy one and later another, so you don't have to purchase everything in one go. You can add on later. And as I also said, we have the analog output with DNC and 0 to 5 volt, or we have the digital output directly into laptop software from AD Instruments. And we have long publication record. I have here just a few data examples. I mean, this is one, I think, which is maybe a bit similar of what the people are, where we're doing the demonstration today. They're measuring changes in cerebral tissue oxygenation, which is the gray line with the scale here. Myocardial tissue oxygenation, which is the red one. And SVO2, the blue line here. Yeah. And you see, if you change, they're all changing. So just something. Hypoxemia, I just wanted to show that some data, I think, from a group who is placing the sensors in 4 different areas. So we have muscle, PO2, liver, the measure arterial PO2. And you see that the muscle PO2 or liver PO2, they respond similarly. Yeah? Here there's some ophthalmology data that just use the vitreous samples. They look at the oxygen consumption in the vitreous sample. So in water there's no oxygen consumption. And in The vitreous treated with some ascorbate oxidase. There's reduced consumption. Normally in the normal vitreous there's a lot of oxygen consumption. Then also I've just picked some data. I mean that's one with bone sepsis. So you see oxygen values of non-treated and treated animals. And maybe that's something else which is more interesting for people here again who do brain. We do offer chronic implantable oxygen sensors. There are some groups in Calgary, in Canada. It's Campbell Teskey, Jeff Dunn, and they're implanting oxygen sensors in the rat for several weeks, and they do connect the animals. Day 1, 2, 3, 4, 5, sometimes even longer, sometimes up to 2 or 3 weeks. They leave the sensors in place. This is the sensor, and that's a glass fiber. In this case, it's 2 millimeters. We do offer the glass fibers at different lengths, so they do order different lengths. They order 4, 5, 6, 7, 8, 9 millimeters, depending on where they want to measure in the brain. And they glue the sensors to the skull. And here they made a picture. As you can see, that's a short sensor that must have been 2 millimeters, and maybe this like 4 millimeters depth. And that's the histology for it afterwards. I'll have a sensor here. It's a bit difficult to reach around, but we'll try. So that they glue the sensor to the skull with dental cement and let the animal go again. So this sensor is only for oxygen, not with temperature.
So this is what's showing in the screen?
Yeah. And this would be the other cable which you see on the picture. That's the connector, you plug it in then, to make the reading. We also do have some other oxygen sensors. We call them large area sensors. I don't have a photo here, I'll just read it through. It has a sampling area of 8 millimeters square. So it's either for larger animals or if you want an oxygen value for a whole organ, so to speak, rather than a punctual measurement like a microregion. Yeah? So for that, these sensors are very, very suitable. They have this size of sensor. It has been placed in the rat, in the kidney cortex, in the muscles, even in the rat. So it is workable and it's preferable for larger animals then. And just to understand one thing, so we have the glass fiber with the tip, and this glass fiber is embedded in this metal. You can see with side windows, yeah? So that whole metal, which you see, is filled with silicon, yeah? So the oxygen has a longer distance to travel to reach that body. So the response time of these sensors is a bit slower. But it's still okay for physiological studies. I don't find them that suitable for brain because the brain doesn't like the size of it. They're a bit wider. I find them a bit more difficult to use in brain. We have some customers who do it, but I find the finer ones easier. Yeah? But for other organs, they're very good. And we do have the same one, just a bit shorter. That's a 1 millimeter square. So it's just a smaller metal end. Yeah. So maybe one more example and then we can move on to questions or the next talk. Here's just a 4-pulse stimulation in the cerebral monitoring. It's very old data. It's probably 15 years old or so, but it's quite nice. It shows that when you place the sensor in a particular area in the brain and you stimulate the animal on the paw, you get an oxygen increase and a laser Doppler increase and temperature increase, yeah? And then you stop, it recovers, and if you stimulate again, you get again a rise and a fall after the end of the stimulation. So, I mean, you have the other data, I think, printed out. That's global ischemia in the brain. So the laser Doppler drops faster than the oxygen, because as soon as you stop the blood flow, there's still oxygen available. So the cells will take some time to consume that. Yeah? And then when you release it, you get a laser Doppler overshoot, and the oxygen is delayed because any oxygen which is coming to the cells who were starved of the oxygen will eat it all. And until you build up again a storage of oxygen, so to speak, which you can see. Okay. So, yeah. I think that's just laser Doppler. Yeah, I think that's the OxyLite Oxyflo talk. Shall we have some brief questions now, or just move on to the next one? What would you prefer?
那这个阶段有没有什么想要问的问题，或是你待会有想到什么后面对不对？那我们先往下一题。Okay, next.
So I'm talking about hypoxylab now, and I'm just starting with the last slide. But I just like the heading of that: defining physiological normoxia for improved translation of cell physiology to animal models and human. Yeah. So there is normoxia, there's physiological normoxia or physoxia, and we're talking about hyperoxia and hypoxia. So, but not to worry, I'm going back to the first slide now, or the second one. So, now people grow lots of cells. I have done that during my PhD 25 years ago. And I did not grow the cells under hypoxic conditions, yeah. But why is it important? So I'm going to compare traditional incubators with hypoxia incubators and introduce the hypoxic workstation. Yeah. So let's start with this. So just going back to basics a little bit. In air, we have 78% nitrogen, 21% oxygen, a little bit of argon, and CO2. At sea level, like I was told, most of the cities in Taiwan, they are more or less at sea level. You will have about 760 millimeter mercury of partial pressure, of which are 159 millimeter corresponding to 21% oxygen. I live in Munich, in Germany. We have an altitude of about 500 meters. If I plug an oxygen sensor into the OxyLite monitor, it will give me 149 millimeter mercury. Yeah, because we have a different pressure. So the altitude of where you are based affects the gas amount, not the concentration of the oxygen. We still have 21% oxygen in Munich, but obviously we have less oxygen available to us. Yeah? And that's already 6.5%. So in air, altogether we have 600 millimeter nitrogen and 160 oxygen. In a standard incubator, a CO2 incubator, you have some, sorry I wrote that wrong, the too close, just water, yeah. So you have 6.2% water. Usually you have about 5% CO2 to keep the pH stable, which results in 140 millimeter mercury of oxygen. And the rest is nitrogen. In air, as I said, we breathe 160 millimeter mercury. If you measure in the lung, we have about 100 millimeter mercury oxygen. The arterial blood carries between 75 and 100, and the venous blood between 30 and 40 millimeter mercury. Yeah? So taking all that together is why we are incubating the cells at 141 millimeter mercury if we have in the body much less oxygen in the cells. Yeah. So that's the big questions I'm asking today. Yeah. We have done it so far because we didn't know that the oxygen values were different in the cells, and as I said, during my PhD I didn't use a hypoxia incubator either because people did not know. But now we do know more, so maybe we should start rethinking how we do the research. I'm not talking about diffusion now, but I want to talk about the Nobel Prize 2 weeks ago. They were looking at HIF-1 alpha, which is constantly produced in the cell and constantly degraded in the presence of oxygen, VHL, protein, and ubiquitin. If one of these three items is missing, proteins is missing, HIF-1 alpha will increase, and it will affect the gene expression in the nucleus. And it will affect all that. So don't worry, we're not going into details, yeah? But, so the HIF-1 signaling pathway is very complex, and we can see if the oxygen regulation is not physiological, it will affect a lot of different signaling pathways and the metabolism. I've just summarized a few things which are, a few genes which are affected from the HIF-1 alpha and the oxygen concentration. It's matrix and barrier function genes. Inflammation, so also if you look into immunology, is affected. So there have been studies with killer cells, T4, T8 cells. Now that you get different responses with under hypoxic conditions, they affect increase of oxygen delivery, angiogenesis, again like you have sometimes tumors, VGF pathways, the vascular tone, oxygen consumption, promotion of anaerobic metabolism, regulation of cell proliferation, apoptosis. So many, many things. And to just summarize what we are doing at the moment, we're growing the cells at a 40 times higher than normal oxygen level in the normal incubators, in the standard incubators, yeah. The physiological tissue ranges from about 5 millimeter mercury to about 75. Like I said before, the oxygen refined in the different tissues in the body. So we would require physiological oxygen concentrations to refine our cell culture. The high oxygen can trigger cellular stress and physiological changes, and it affects differentiation, growth factor signaling, and other cellular processes. Yeah? The existing hypoxia incubators and workstations are cumbersome, which means they are slow to reach oxygen set points, costly to run, and they use an oxygen sensor which is working with percentage oxygen, not with partial oxygen pressure. So which means if